And okay, so now Bogdan is going to present the final lecture.
Okay, yeah, so I guess as there was a question in the chat, which sort of presaging what I'm about to say, you know, if you've got a local or gauge symmetry, so far we've been talking about these terms interchangeably because we took the view that the manifold, the space-time manifold, be it three-dimensional or four-dimensional, is just is essentially doesn't have any boundaries. But now if you have a space-time with a boundary, then things can be a little bit more subtle. So first thing, you have to pick some boundary conditions for your gauge field. And then you have to ask yourself, what are the local symmetries that are compatible with these boundary conditions? So if I picked some really weird boundary conditions, I could break all gauge invariants. You know, it could be if I picked some totally crazy boundary conditions. Now, in fact, once you have a boundary, we tend to think of gauge symmetries as, sorry, always goes to the eraser. We tend to think of gauge transformations as being trivial on the boundary, so that they don't change the boundary condition. But sometimes there could be local symmetries which act non-trivially on the boundary and yet still preserve the boundary condition. So this distinction is particularly sharp when you have some time-independent local symmetries which are not zero on a boundary. So imagine you had some configuration where in the past time where you defined your Hilbert space, you're in Hilbert space, you had some local symmetry which was acting on the boundary, but it was time independent. So because it was all in the long distant past or something like that. So, well, in that case, of course, the way I've just said it is that these local symmetries act on the Hilbert space of states. And so that means the Hilbert space, of course, has to form some representations. And this happens, for example, as was being alluded to in the chat, in 3D Chern Simons theory. So the sort of classic example from the late 80s is to consider Chern Simons theory on the real line, call that time, and have a disk. And we have a solid disk with an angle theta and a radius r, and we put some Dirichlet boundary conditions on the boundary of the disk. So the equations of motion tell you that the gauge field has got to be pure gauge. In fact, we can see that a little bit more. I fleshed this out a little bit more in an exercise. You can show that the Chern Simons action takes this form, where you see the AT component just acts as a Lagrange multiplier, which tells you that the gauge field in the remaining two directions has got to be zero. So you can solve this condition by picking a flat gauge field. So I'm going to, so because we're on a flat disk, right, you can only have these pure gauge, there's no topological issues. So you can only have these pure gauge configurations. Okay, so now you just plug in this solution back into your action, and what do you get? And this is the exercise I would advise people to do, is you end up with effectively like a boundary term, something that just lives on the boundary of the disk, on the theta and the t coordinates. And then you have just from the a cubed term in the Chern Simons action, we have this Wess-Zumino-Witten term. So this is a chiral kinetic term. So I'm not going to have really time to explain it. It's not quite, if you do the Wick rotations right, it's not quite a normal kinetic term. It's a chiral kinetic term. But this is the famous example of having a boundary in Chern Simons theory with Dirichlet boundary conditions, and the theory on the boundary will turn out to be a Wess-Zumino-Witten model. And that's because you see there's this local, so this action is invariant under left and right multiplication. In particular, it's invariant under this left multiplication, where I pick any element in the group, but not just an element in the group, but it can be it can depend on the coordinate theta. So this element here is not just an element of the group G, but it's an element of the loop group of G, because I have an extra circle. So what we're finding is that the Hilbert space forms a representation of the loop group, and then you have to work hard, and people did. I'm not going to do that here, but with a bit of extra work, you can show that when you quantize this, you end up with a Kac-Moody algebra, where the Kac-Moody current A theta is just the theta component on the circle S1. So this is just by way of kind of inspiration for you. What you're seeing is a kind of holography, a holography before Maldacena. It's one of these cases. There are a few where that existed, but here it's quite concrete, right? So you could imagine now having a cylinder with two endpoints, one at 0 and one at infinity, picking a chiral boundary condition like this on one side, an anti-chiral boundary condition on the other side. So the anti-chiral gauge field here is 0, and the chiral gauge field on the other side is 0. And you've got a topological Chern Simons theory in the bulk connecting these two CFTs. So that's kind of an inspiration for us, I guess. And we can try to see if, by introducing boundary conditions into the four-dimensional Chern Simons theory, whether we can come up with this kind of picture. Well, okay. In the previous lecture, we talked about a one form like this, which was just 1 times dz. But Costello and Yamazaki, I guess last year, argued that there is that you can generalize this, and you could consider very general one forms, which have got some zeros and some poles. Now, in general, you could imagine families of these one forms, where you get higher order poles appearing as simple poles join up, or higher order zeros appearing. And the only ones that you have to worry about separately to figure out what's going on are simple zeros or double poles, and also simple poles, but these ones I'm not going to talk about today. So everything else can be built up from that just by, for example, here I could get a double zero if I send Z0 to equal Z1. Okay. So why is this sensible? Well, it's only sensible. So if all I did was I said that omega has got these zeros and poles, this would not define a consistent theory. But if you pick just the right boundary conditions, whenever omega has got zeros or poles, then it turns out that the theory is still consistent. And here's a simple example, right? So if we are near z equals 0 or infinity, we're going to, in other words, if we are near the double pole of omega, we are going to say that all the fields have a Dirichlet boundary condition, right? They have a 0, a simple 0. Why does this work? Well, one simple way is you can expand the action near this point, be it 0 or infinity in this case, but in general some other point. And so you expand it, omega has got a double order pole, and the gauge fields have got simple zeros, so those cancel. So the theory is well defined in the neighborhood of your double pole. Another way of saying it is that this kinetic operator is well defined. Okay, how about near a simple 0? Well, here you choose. You either set a w equal to 0, or you set a w bar equal to 0. And you say that everything else, all the other components of A, are regular. And again, you can check that if omega has got a simple 0 here, and a w has got a simple pole, then the other guy does not have is regular, so it starts off with the 0th power. And then again, the function, the integrand is well defined. So we could, yeah, as I say here, we could also consider simple poles, but today I'm not going to do that. those are more directly related to how you get the Vezzumino-Witten theory. So I'm going to talk about the principal chiral model here, but if you considered instead simple poles, that's how you would get the Vezzumino-Witten model from the 4D Chern Simons theory rather than from 3D Chern Simons. So okay, here's the plan. I'm going to try to find a gauge field A, which has got these boundary conditions. Near 0 and infinity, this is, remember, where omega has got its double poles. Omega has got double poles here. I'm going to set the A is equal to 0, and near the zeros of omega, I'm going to set AW to 0 at one and AW bar at the other to have a simple pole. So the plan is, let's find this gauge connection and let's write out what the action looks like. Well, AZ bar, we can think of it like this. Let's for a moment ignore that we have got the W and W bar directions. So we just have got this holomorphic bundle on CP1. And in fact, you can think of it as a family of holomorphic bundles in W and W bar. Now, I guess there's some standard theorem in algebraic geometry that tells you that these bundles, these holomorphic bundles are trivial. And so what that means is you can compare, you've got some fiber of the bundle near 0 and some fiber near infinity, and you can just compare the two fibers. Okay, what does the fiber look like? There is some map, some group valued map that tells you what the relationship between the fiber at 0 and its infinity is. So that defines, that's the comparison map. And there's no reason why you should just compare the point 0 at infinity. You could compare any other points, right? There's no reason to choose 0 and infinity. And that's how you extend to a function, to a group valued function sigma hat, which near z equal to 0 is just the identity, and near z equal to infinity. So here you're comparing the fiber at 0 with the fiber at 0, and here you're comparing the fiber at 0 with infinity. So that guy gives you sigma, and this guy gives you identity. And that's going to be, that is what we can use to define what AZ bar has to be. AZ bar effectively has got to look like this. Because, well, it's just from this construction. Okay, so the only other thing that I'm going to do, it's a technical point that comes up in some of the exercises, so I'll just highlight it here, is that you can choose, there are many, obviously depending on which gauge you're working in, right? This is some particular gauge choice for AZ bar, and you can choose sigma hat to be invariant under rotations of Z. So Z being rotated like this, then you can choose it to be invariant under AZ bar to be invariant under such rotations. Okay, now notice that we're already starting to see some nice things. Because sigma hat here is proportional to the identity, AZ bar will be equal to 0 at Z equal to 0. And at infinity, at Z equal to infinity, this guy here, the sigma hat, is independent of Z and Z bar, and also will give you 0. So some of the boundary conditions that we have, like this one here and this one here, we have solved just by introducing this sigma hat. All right, let's carry on. Maybe we'll be lucky, right? Maybe we should just set the remaining components of AW and AW bar, maybe we should also set them to be just pure gauge sigma hat. Turns out that's okay at Z equal to 0, and that's okay simply because near Z equal to 0, sigma hat is just identity. So derivatives of identity give you 0, so that's great, but you cannot satisfy the boundary conditions at Z equal to infinity with this choice of AW and AW bar. See, near Z equal to infinity, sigma hat is given by this non-trivial function sigma. Remember, sigma was a function of W and W bar, right? This is how we defined it. And, well, clearly this is not 0. So you need to correct this by adding some extra term to your connection so that you get something that satisfies the boundary conditions that you wanted to. And the thing that you have to add, so this is another exercise that you should go through and check, is this particular weird combination. So look, there is a part here which is just a current made up from sigma, and then we conjugate it with sigma hat. And you have a dW component and you have a dW bar component only. So our final gauge connection, which turns out to satisfy all the boundary conditions, is a sum of this A hat and A prime. And the A prime part, I guess you can see, has got poles, one at Z0, one at Z1. The Z0 pole is in the dW component, and the Z1 is in the dW bar component, and that's exactly what we wanted. We wanted a pole here in just AW and a pole here in AW bar, so those poles come from A prime. And these remaining zeros, you choose them and you choose A prime precisely in such a way that it cancels the non-zero contribution that A hat has here. Okay, so all we do now is we take our solution and we plug it into the action. So what does that look like? Well, you have an A hat and you have an A prime. So the action will be the action for the full connection will be the 4D Chern Simons action for one, for the other, and then there will be mixed terms. So here is, for example, one mixed term that you get when you take two A primes and one A hat. If you instead take one A prime and two A hats, you get this term together with some ADA term. So there is an A hat A prime and an A prime DA hat term. And I've written those together to make up an F hat times an A prime. And I've got this term here, which is a total derivative, because when I write the term in this way, I get a total derivative term as well. So I can throw out the F hat term quite easily, simply because A hat, remember, was pure gauge. So by definition, F hat is 0. Now, it's a small exercise. You can also show that this term is equal to 0. The A cubed term, that's quite easy to show. So when you have this term in the action, well, that's 0 just because A prime has got only a W component and a W bar component. So that's fine. And a little bit more work is required to show that the A prime dA prime term is also 0. And here you're going to have to use these nice identities, which I'm sure you all know, that if you take the Z bar derivative of 1 over Z, you get a delta function. And this delta function, in this case, when we've got this term here, it multiplies our form omega. And remember, omega is near Z0, it has a 0, so it's Z minus Z0. So this whole term is really something like Z times the delta function of Z, which is equal to 0. Okay, so it's a little exercise you can do to show that this term vanishes. This term also vanishes. And the term I really want to concentrate on is this total derivative term, because that really shows the sort of thing that ends up happening over and over again in these calculations. You might think that you should just throw this term away, right? But this term is not exactly a total derivative because you're multiplying by this one form omega, and now our one form omega has got some poles. It has double poles at Z equal to 0 and infinity. And so in particular, there is some identity like this, that the d bar derivative of 1 over Z squared is something like delta prime derivative of 1 over Z. So here is when you take this term and you integrate by parts, you will end up with two delta functions or derivatives of delta functions. Okay, so this term gives you non-zero answers, and remember this term involved a hat and a prime. So here is the expression from a hat, a prime, the W bar and W component. So you're just plugging in now. And here is the one from WW prime. Now, in the gauge that we're working in, remember sigma hat was identity near z equal to 0. So this guy is actually equal to 0. But at z equal to infinity, sigma hat was like sigma. So you got a non-zero answer. And it's this guy that gives you a non-zero answer. So the 0, in the gauge that we're working in, 0 does not contribute. At infinity, however, you pick up the poles over here and over here, and you get a term that looks like this. And this is precisely the standard kinetic term that you would have in the principal chiral model. So then you can work a little bit more, and you can show that this term is 0, and you can show that the action evaluated just on a hat gives you a WZW, like a three-dimensional WZW term, because we're working in this gauge with U1 rotational invariance. Okay, so what have we done is we've taken four-dimensional Chern Simons theory. We've picked this one form which has got some second-order poles and first-order zeros, and we've reduced the theory down to 1 plus 1D, subject to some boundary conditions. And we've arrived at a principal chiral model with a WZW term with, I didn't write it down here, but maybe I did. I think that's a mistake. I think this should be Z1 plus Z0 with different couplings for one and for the other. So you can tune them, and all of those, as we discussed yesterday, are classically integrable. So how do I see this classical integrability happening here? Well, away from singular points, we could pick a gauge. We don't have to work in the Lorentz gauge like we did in the last lecture. We could pick a gauge AZ bar is equal to 0. In this gauge, here is just the equation FWW bar equals 0. So that's just a normal equation. But the other equations, FWZ bar, they, remember now that AZ bar is equal to 0, they reduce to the condition that AW and AW bar are just functions of Z and not of Z bar. But this is precisely how we define the lax operator, the lax connection. So AW and AW bar are holomorphic in Z, and they're precisely the lax connections that we had yesterday. Now, of course, we could work in other gauges. We don't have to work in this gauge, but the thing that we're after in the end is to figure out what are the right gauge invariant observables, and so the Wilson lines in this quantum theory, which are going to actually carry all these charges. Okay, any questions about this? So now I want to take sort of the final step in this story from what's known so far, and show you how this kind of construction can be generalized to the Metsayev-Zeitlin superstring. So I'm going to do this in 3 steps. First, I'm going to write down what the Metsayev-Zeitlin coset sigma model looks like. And then I'm going to, in this construction, so I'm going to have to find some omega and some boundary conditions that will give us the Metsayev-Zeitlin coset sigma model, so no worldsheet metric. Now this sigma model, yes, it's classically integrable, but it's a bad sigma model, right? There are no, as we discussed, the kinetic terms for the fermions, they're not all there, right? There are no conventional kinetic terms for fermions, so it's not a nice sigma model. But we can cure it by coupling it to the worldsheet metric. And so I'm going to explain how you get the worldsheet metric to how you could introduce a worldsheet metric into Chern Simons theory by generalizing it into something called Beltrami Chern Simons theory. And then I better show you that the resulting Beltrami Chern Simons theory has got this weird extra kappa symmetry, which makes everything really nice, right? Which cures any sickness that the coset sigma model may have. Okay. So let's do that now. Well, we're going to start with our favorite gauge group for ADS5 cross S5. And because secretly we want a Z4 coset to appear somehow, we're going to start with 4 copies of this. Now, a comment that I already made to Shota was that, you know, there is no framing anomaly here because the dual Coxeter number is 0. So you really can treat the coupling constant that appears in this 4D Chern Simons action as just an honest to God coupling constant. And the Wilson lines really are nicely defined. And what we're going to do is we're going to take, so this is a bit of a prescription, right? In principle, I guess I didn't say this up front, but basically you give me an omega with these types of boundary conditions, and classically at least, you can write down a zoo of integrable sigma models. What's more, you could be even on, not defined on the Riemann sphere, like I've been doing it on CP1, but you could be on some higher genus surface, and Costello and Yamazaki, they discuss how you can glue various surfaces together with some cuts, and you get these higher genus integrable models, which just did not exist. No one really thought of them, and it's essentially huge infinite families of classically integrable sigma models. But what we're going to concentrate on here is one that hopefully leads to a string theory. And the construction goes like this. This is our gauge group. We're going to require that there are 3 plus 3 zeros of the one form. And those zeros are going to be labeled by Q's and Q twiddles. And there are going to be 4 double poles. And at these double poles of the one form, we have the usual Dirichlet boundary conditions, while at the 3 zeros of one kind, we say that AW is 0, and at the 3 zeros of the other kind, we say that AW bar is 0. Okay, I mean, it's a slightly elaborate construction, but that's just because the Metsayev-Zeitlin sigma model is slightly more elaborate than just the principal chiral. So this I'm not going to go over in detail now, but the construction really mirrors exactly what you do in the principal chiral model. You find some A hat, which is pure gauge. It doesn't quite satisfy all your boundary conditions. You have to modify it in some way. And you modify it by adding this A prime, which has got only non-trivial components in AW and AW bar. And it's got simple poles. AW, remember, will have simple poles at all the Q's and AW bar at all the Q twiddles. And I'm going to call the residue of those poles, I'm going to label the residues by JK at W. And so because this is Lie algebra valued and because this is a flat connection, you can write them, these residues in this form. So basically, you can choose a gauge for your sigma hat such that near each one of the P's, it looks like sigma K, and Kevin and Masahito further fixed the gauge so that near the last P, sigma hat was equal to identity, just like they did in the principal chiral. Okay, in any case, you can find these configurations and then you can plug that into your action and you get some integrable sigma model. What is this? Where is the sigma model part of it? Well, it's written in terms of these currents JK alpha. So near each one of the points PK, you have a current, and the action, if you look at it, it's quite complicated, right? It's quite involved. It has different terms, different couplings between these different currents, and it is integrable because secretly there is a Lax pair for it, or not so secretly. You can write down a Lax pair for it that's equivalent to the equations of motion. Now, it's a little bit helpful to actually undo this gauge choice So this is for those that are just interested in the technical details. And in fact, there is a way to write down the same action in a way that there are really 4 currents, not just 3 currents at the 4 different fixed points. And that's slightly more symmetrical. But in any case, at this point, you just have some integrable sigma model. And what we do now is we send the coordinates pi, which were up to now arbitrary, we send them to the 4th roots of unity. So 1, I, minus I, and minus 1. And we have 2 choices. We can either send all the q's to 0 and all the q tildes to infinity, or we can send 2 q's to 0 and a q tilde to infinity. Those are essentially the only 2 inequivalent choices, which leave your theory. So when you do these 2 things, why am I doing that? Because at that point, the theory has a certain Z4 symmetry. So this sigma model before, remember, was a sigma model on a PSU 224 to the power 4. I don't actually want 4 copies of PSU 224. I just want 1 copy of it. And so this Z4 is going to eliminate those copies, but it's going to do a little bit more than that. So let's go over that slowly. So here is, if you want the ith component.
Sorry, Bogdan.
Yeah.
Was there a typo for the choice B?
Yes. Thank you. That's right. So you want to send half of the q's to 0 and half to infinity, and there's essentially 2 inequivalent ways to do that. I mean, I suppose you could send all of them to 0, but I'm not sure. I guess it'll just give you something else, some other integrable model. I haven't thought much about it. Okay, thanks. So now I'm going to orbifold this theory. So my gauge group is 4 copies of PSU 224. And the orbifold action will act like this. It's kind of obvious on what it does on the gauge symmetry. It just takes the ith copy and maps it to the I plus 1 copy, while at the same time acting with the Z4 orbifold. So this is a Z4 action on 4 copies of PSU 224. And what's more, we're going to act on Z. So we're going to send, so I keep writing square root of -1 because I just realized that I use the index I for other purposes, right? But I'm just multiplying by -I. So it's a 90 degree rotation in the Z plane. And for those of you that work on integrability, you'll recognize that this is precisely how the Z4 symmetry in the Metsayev-Zeitlin string acts on the spectral parameter. Anyways, okay, so that's a technical comment, but here is, so with this choice of P's, of the location of the double poles, and either of these 2 choices of Q's, there is a Z4 symmetry, and I can mod out by it. And the Z4 symmetry acts very simply on these currents. It just takes the first current into the second current times omega. So you see, it doesn't leave, you might have thought, if I didn't have this omega acting here, it would leave 1 copy of PSU 224 invariant. But actually, when you write down the sigma model with this omega acting on it, you don't end up with a sigma model on PSU 224, you end up with a sigma model on PSU 224 with this extra gauge symmetry still left unbroken. So that's how you get a sigma model on this coset. And depending on whether you chose the choice A or B for the Q's and Q tildes, you end up with the Berkovits pure spinner sigma model. So this is a sigma model which, as well as having a J2 term, kinetic term, it also has a J1, J3 kinetic term, alpha, beta, gamma, alpha, beta. And this guy here gives kinetic terms to the fermions. But if instead you pick choice B, so you send 2 of the Q's and 1 Q tilde to 0, then you end up with the Metsayev-Zeitlin sigma model, which of course is a bad sigma, but it is the one we want. Okay, so a kind of slightly cryptic comment, but something that always bothered me about some of these integrable constructions was that there are very simple generalizations that Charles Young, wrote down some years ago, of the Berkovitz string sigma model rather, when you don't have Z4 symmetry, but you have Z2n symmetry. You can imagine how you can very simply generalize this. And somehow there were never any integrable sigma models of the Metsayev-Tsaitlin kind written down in this way. And it seems now you can do this with this construction, because of course, instead of having 4 copies of PSU224 and having 4 double poles, I could set up any even number of them and play this kind of game here. So that's kind of a nice little curiosity where always there was this little gap in the literature, and I was always thinking like, well, someone should be able to write down the analogs of these things that Charles did, and indeed one can do this with this construction. Okay, but that's sort of more to satisfy some little thought in the back of my head. But what I want you to really just take away from this, if you haven't fully followed the details, is that in the case of the Metsayev-Tsaitlin sigma model, we end up with the following boundary conditions at z equal to 0. So AW has got a second order pole because 2 Qs go to 0, and AW bar has got a first order pole because 1 Q tilde goes to 0. And the opposite thing happens at infinity. So AW and AW bar have different order poles at 0 at infinity. And this is going to be kind of the important thing. So I want to pause here and see if people have questions. Okay, good. So how do we introduce a metric into this? We better get a metric, and we better get kappa symmetry, because otherwise this sigma model is not very nice. Well, see, it's a very strange thing to, I mean, the whole Chern Simons construction assumes that you don't have a metric, right? Everything is written as an exterior, the action is written in terms of some exterior derivatives. It's written in terms of an epsilon tensor. That was the whole point of Chern Simons theory, is that, okay, modulo gauge fixing, we don't have a metric appearing anywhere. So why would I want to introduce a metric into this sort of topological type theory? Well, the whole point is that that statement I've just been making is true really when I don't have a boundary. So, you know, for example, you can check very simply that if you take the gauge connection and you do a diffeomorphism to it, right? You plug that in and the action is invariant. And it's kind of completely trivial because, of course, there is no metric. But if there are boundary conditions, they can break diffeomorphism invariance. So in the Metsayev-Tsaitlin Chern Simons theory, which said that AW bar has got a first order pole at z equal to 0, but AW has a second order pole. Now look, this diffeomorphism transformation potentially mixes up AW and AW bar. It'll give you some stuff here, some non-trivial stuff here. Right? Now, that's clearly not compatible with these boundary conditions. So let's see that in a little bit more detail. What I'm trying to say is that with these boundary conditions, you break diffeomorphism invariance on the boundary. But let's just see that nice and slowly in some detail. And we can, you know, instead of writing out pages and pages of calculations, let's think a little bit about where is this lack of diffeomorphism invariance going to come from? Well, it's going to have to come from the part that's singular in AW and AW bar near z equal to 0. Because any part that is regular, well, it doesn't have this kind of problem. So I'm only going to have to keep the polar part in both cases. And the only place that can be non-diffeomorphism invariant is if I take a diffeomorphism variation like this. So I only say that I vary by this polar part. Okay. Now let's just plug that in. I mean, you could plug in the whole thing, but then there's lots and lots of terms which are 0, and these are going to be the non-zero parts. So if I vary the 4D action, there's only really two terms that contribute. The AAA term doesn't. It's just the kinetic term ADA that contributes. So okay, you vary A, you vary dA, you integrate by parts, and you get a term like this. And now look, this guy here, when you integrate by parts, gives you essentially a total derivative. But as before, we have a non-trivial form omega, so it isn't just going to give us 0. We're going to, perhaps, there might be a residue we will have to pick up. So this polar part, remember near, where were we? Near z equal to 0, AW had a second order pole, and AW bar had a first order pole. And near z equal to 0, omega had a third order 0 because 2 of the q's and 1 q tilde were going to 0. So we've got a third order 0 here. We got a third order 0 here. And the boundary contribution better have a fourth order pole so that it cancels the third order 0 here, and that I just have a simple pole. That's the only term that can give a non-zero answer. Now, something kind of nice happens, because that term is, you can convince yourself, because the whole current is Z4 invariant, you can actually convince yourself that the polar part of the gauge field involves the -1 eigenspace and the -I eigenspace of the Z4 automorphism. Because remember, omega sends Z to -I times Z. So this combination here together is invariant under omega, and this combination is invariant under omega. So you actually know that the residue of the pole has got to be precisely the J2 part that I had in the Metsayev-Zeitlin action, and the first order part is going to be, okay, one of the fermionic parts. Okay, but why am I saying all this? Well, you see, this is non-zero now. We've convinced ourselves that it's non-zero, and it's non-zero precisely in a way that looks like the Virasoro condition. So the lack of gauge invariance is looking very familiar. The lack of, diffeomorphism invariance is looking very familiar. Now my job is to fix that lack of diffeomorphism invariance by introducing some extra field, which is going to play the role of the worldsheet metric. So these are these Beltrami fields. And what you do is you say, I'm going to twist the complex structure a little bit by this Beltrami field. That's why I guess it's called the Beltrami field. So instead of treating d bar as my BRST operator in the Chern Simons theory, I'm going to twist it slightly by a Lie derivative term. So I'm modifying my action to include this change of complex structure in the W bar and Z bar directions. Remember, the Lie derivative has got to be along a vector field. dW and dz are vector fields, and this is the field BW bar. So you could ask, why am I doing this, and why have I not done this before? Well, the reason no one ever bothers doing this in normal Chern Simons theory, right? Like everything I've done here, you could do in just normal 4D Chern Simons theory from the previous lecture, or you could do something very similar in 3D Chern Simons theory. So why has no one tried doing this before? And that's because there is this Cartan's homotopy formula, which relates a Lie derivative to the commutator of the exterior derivative and the interior product with the corresponding vector field. So what are you doing? When you're adding these terms to the action, you're modifying the action, but you're modifying it in a BRST exact way. So you're adding a BRST exact term. And indeed, you can show, so I leave that as an exercise, you can show that in components, the term, the Beltrami coupling looks like this. It involves AW and an exterior derivative of A, and a field redefinition. You do this field redefinition, you plug it in, and you recover back the 4D Chern Simons action. Okay, so that was a lot of activity. Let's just pause a bit. I've changed my action. I've introduced by a BRST exact term. That was a complete waste of time, is what I've told you, because I can get rid of that whole new term just by redefining AW bar in this way. So this is why no one ever does this in Chern Simons theory or in 4D Chern Simons theory, because a field redefinition just brings you right back to the original action. But this field redefinition, you're not allowed to do it when you have the Metsayev-Zeitlin boundary conditions. Again, it's the same thing. AW bar has got a first order pole, AW has a second order pole, the field beta better be regular, and so you cannot make this redefinition. So what I'm saying is that with the boundary conditions that you need for the Metsayev-Zeitlin sigma model, beta, this coupling to beta is actually a new degree of freedom. You cannot just redefine it. And then you can ask yourself, okay, great. So that is, now I have the Beltrami Chern Simons theory. So there's some new field beta, and not just the connection. It has some non-trivial dynamics caused by the boundary conditions that I've introduced. And let's see what its equation of motion is. Right? In the equation of motion of the Beltrami, the calculation, you can just guess what it's going to be, right? The Beltrami precisely made sure that we had a diffeomorphism invariance. We restored diffeomorphism invariance. And so its equation of motion has got to be precisely the thing that, up to a minus sign, that we saw that there was lack of diffeomorphism invariance. So I won't go through this. I've spelled out the calculation in detail here. But you get precisely the Virasoro condition coming out of the Beltrami equation of motion. So that's quite nice, right? So now we know how to couple a metric to this a world sheet metric to this four-dimensional Chern Simons theory. And this part of the story, I guess I should stress, is quite general, right? You could give me some, I focused quite a lot on the Metsayev-Zeitlin superstring. But if you just wanted to consider a sigma model with a world sheet metric and you wanted to get some Virasoro out of it, then you could do this, at least for the integrable sigma models, just in relative generality. Okay, so in the last few minutes, I'll say a bit about kappa symmetry, and hopefully this will go sort of right back to the first lecture. Maybe if you remember the first lecture yesterday, you'll see some formulas that look very familiar. So normally, as I said, you set the gauge variations on the boundaries to vanish. That's the simplest thing you can do. That makes sure that the boundary conditions are unchanged and that you don't break any gauge invariance. But we're going to not do that. We're going to allow gauge transformations which are singular near z equal to 0, and we'll only allow simple poles. So because everything has to be z4 invariant, if I have a 1 over z, that the z4 automorphism multiplies that by minus I, which means that I'm only allowed to have the third eigenspace of PSU224 appearing. So this is fermionic, right? So I'm going to allow singular fermionic gauge transformations. So that should already sound a bit like kappa symmetry. And what I expect is if I allow such gauge transformations, I expect that the action will no longer be gauge invariant, right? I'm saying something quite simple. Normally, we set gauge variations to be 0 precisely because we want to keep gauge invariance on the boundary. Now I've been naughty, I've done something I shouldn't have done, right? I've allowed a singular gauge transformation, and lo and behold, the action is no longer gauge invariant. Where is it not gauge invariant? It's not gauge invariant precisely at the point where the transformation was singular. So you can go through this in detail, but you end up with, you vary the action and you end up with some terms which look a little bit like the sorts of terms we saw before, namely you have a z cubed and, for example, a z, and here you have a, so overall you have in this first term, you would have something like z squared dz bar 1 over z cubed, and so that's like z squared delta, second derivative of the delta function, and so that is not equal to 0. Right, by integrating twice by parts. Right, we're doing everything just in the neighborhood of z equal to 0, so these are quite simple to do. And when all the dust settles, you see that the action, the Chern Simons action, is no longer gauge invariant, and it's no longer gauge invariant by a term that I'm hoping is familiar to you, or at least is familiar to those of you that went through the pain of the first lecture. This is exactly what we had in when we did the kappa variation of the matter fields in the Metsayev-Zeitlin superstring. This, if I set psi here to be of this form, just like we did in the Metsayev-Zeitlin superstring, is exactly how the matter fields, the currents, vary under kappa transformations. So, in the special cases where the sphere's identities hold, you can rewrite these variations, just like we did before, in terms of these double traces with this upsilon guy. And as long as the Beltramis, which sort of correspond to the metric, transform non-trivially under the kappa transformations in this particular way, the whole action becomes kappa symmetric. So what have we done? We've taken 4D Chern Simons theory, we've given it some, we've picked a particular gauge group, we've modded out by some Z4 symmetry, and we've obtained a string theory, a Green-Schwarz type or Metsayev-Zeitlin type string theory on ADS 5 x S5. With, and we've shown how the kappa symmetry and how the diffeomorphism invariants, how you can think of them in, from the Chern Simons point of view. So I think there's a lot of work to do, and I haven't really written a set of conclusions because I'm hoping that, well, there'll be some questions here and that maybe people will be inspired to keep looking at this. I think what would be really nice is to understand more fully how to quantize this gauge 4D Beltrami Chern Simons theory, and to understand what are the correct kind of perturbative calculations to do here, to not just see the integrable structure, but to see the string theory emerging. So I'll stop here. Thanks.
Thank you, Bogdan, for a beautiful set of lectures. Questions? Maybe I can start. So you said, so I understood that in order to have non-trivial action for the Beltrami fields, it was important that AW and AW bar had different boundary conditions.
Mm-hmm.
So what happens to if you consider instead pure spinor superstring?
That's a good question. I don't know. You'd have to go through this calculation a little bit more carefully. Sorry, not this calculation, the previous one.
Mm-hmm.
So I'd like for it to still remain non-trivial, but I'm a little confused now. Why that would be? Let's see. Yeah, you would have to, sorry, I'm not going to be able to do this live at the moment, but you would have to just, so the argument about the field redefinition is quite a quick argument. You should check a little bit more explicitly. So maybe I can check a bit more explicitly offline whether this term, these guys are zero or not. I mean, I don't see why there shouldn't be a metric in Berkowitz's case, but yeah, I think I would have to figure out why I can't do that field. So I expect something like this to be non-zero still, but then I would have to check why the field redefinition fails. Maybe it's more subtle, maybe it's a global issue, that you can't match the z equals 0 and z equals infinity parts or something like that. I think that's a little bit less clear. But I think something like this part of the calculation I would expect to hold still. So I'd venture that you can still add a metric to the Berkowitz case as well.
Any other questions about any of the lectures by Bogdan?
Can you tell us a little bit what are the next things you can do with this theory? So now, well, you tell us the story of integrability, and now there is this beautiful structure. You recover many of the things. So what is the new things one can do with it?
What I'd really like to do, and so now, I'm just going to sort of think a little bit, allow myself to think a little bit more freely, right? I don't know if I can necessarily do all these things, but the thing that is inbuilt are all these conserved quantities, right? They are just normal symmetries of the sphere and these observables. So I suppose if I wanted to be really annoying to the integrable holography approach, I could say, well, do you really know that quantum integrability is preserved? I mean, it's sort of a technical problem because, we have a lot of numerical and analytical evidence that it's true, but here, these symmetries, these integrable symmetries, and you can check whether they're anomalous, relatively, once you quantize the sphere correctly, you can check that they would be preserved because they're just simply the usual symmetries. Like I showed you, these things come from some anomalous diagrams at one loop, sometimes maybe a two loop or so on, but they relatively straightforward. Whereas usually it's quite hard to check whether a theory is genuinely quantum integral. So that could be one thing that I think would be quite nice. If I want to be, even more optimistic and brave, why not? Let's try to think blue sky stuff here. I don't know. I'm not promising anything, but there should be some formulation of things like vertex operators for these backgrounds, right? There should be deformations that you asked about yesterday. If this is really the string theory, then I should be able to deform away from an integrable theory, right? At least locally, I should be able to turn on some marginal operator that takes me from the maximally supersymmetric ADS5S5 background to some other solution, another nearby solution. Can I at least perturbatively understand such things? That's the kind of questions you could also ask.
I see, thanks.
So let me ask another question, although we have a bit late already. But so So is it possible to embed for the Chern Simons theory to string theory or something like topological string theory?
I think there are some papers on this, right? And I don't know how directly, how explicit that construction is for a general omega. But I think there are papers that, this is a paper that Kevin and Yunya Yagi wrote. Mm-hmm. And I think they refer to another paper there. I can try to put up some comment on Slack. And I think there was some talks also that Nikita Nekrasov gave at some point, which kind of looked at some kind of topological twisting of some 6-dimensional Yang-Mills theory and some omega background. But I don't know. As far as I know, that's mostly in the case when omega is dz. But maybe I'm not. But maybe people have thought about this more. But yeah, I think that'd be a nice question to ask, right? And you could even ask it in slightly simpler settings. You could ask it for the principal chiral model, or you could ask it for some WZW model or something. You maybe don't go for the full superstring straight away. But yeah, perhaps there's something to be explored there as well. So lots of open questions.
Any other questions? Well, I guess we can anyway continue in the Slack. Sure. So yeah, so let's thank again Bogdan for a beautiful set of lectures.
Thanks. Thank you.